Hello. This lecture we're going to talk about the closure properties of context-free languages. Remember that we had done the same discussion regarding the regular languages, and we had talked about the closure properties regarding certain operations on regular languages. Now we'll try to do the same thing for context-free languages. Let's first start with our first operation, which is union. So in terms of closure, we want to know the following. Let two languages, A and B, be context-free languages. Is their union, is the union of A and B always a context-free language? This is the question that we want to answer as far as closure properties regarding union is concerned on context-free languages. We can easily see that the answer to this question is yes. And the idea is as follows. The idea is simple. Since the language A is a context-free language, then there must exist a context-free grammar that generates this language, and the same is true for B as well. So there exist context-free grammars. Let's give them some names. Let's give the starting variable of the context-free grammar for the language A to be SA, and let SB denote the starting variable of the context-free grammar that generates the language B. So there must exist such context-free grammars. Now we can easily construct a context-free grammar for the union, A union B, easily as follows. We will just need to generate, in addition to the rules of the context-free grammar for A, and in addition to the rules for the context-free grammar for B, we will only need to introduce one more rule with a new starting variable S that goes to SA, where SA is the starting variable of the context-free grammar for A, or SB. Only two new rules are introduced, and then we can, underneath, we can write down all the rules regarding SA and all the rules regarding SB. This just says that anything that you can generate with the starting variable of the grammar for A, you can generate those strings for the new grammar as well, and the same is true for any string that is generated by starting with the starting variable of SB. All those we can also generate by the new starting variable S. Thus, this new S and the whole of the grammar, including all the rules of the grammar A and B, will give rise to a grammar that will generate A union B. We will write down all the rest of the rules for grammar A and for grammar B, and the new CFG generates A union B. This means that if A is context-free, B is context-free, then we can easily design a context-free grammar that generates A union B as well, which will mean that A union B is also context-free. This implies that context-free languages is closed under the union operation. Now we can try to do the same thing for the other operations. Let's now consider the concatenation operation. Again, the question, we can pose it as follows. Let two languages, let A and B, be two context-free languages. Is their concatenation, A concatenated with B? Remember that we denote the concatenation operation with a circle or a dot. Is A concatenated with B always a context-free language as well? Again, our answer to this question is simply yes. the main idea is that if A and B are context-free languages, then there must exist context-free grammars that generate them. There exist context-free grammars generating A and B. Let SA and SB be these grammars be their starting variables. Then we can easily create a new grammar for A concatenated B by introducing the following rule: S goes to SA followed by SB. And then for the rest, we can write down the rules corresponding to SA and the rules corresponding to SB, and S will generate any string generated by SA followed by any string generated SB. Thus, the whole grammar will actually generate any string inside A concatenated B. Therefore, new CFG generates the new language A concatenated with B. So again, we can say that the context-free languages are closed under the concatenation operation, since for any two context-free language A and B, their concatenated version A concatenated with B is also a context-free language. For the next operation, let's consider the star operation. The question is, are the class of context-free languages closed under the star operation? Again, we can pose it as follows: let A be a context-free language is A star, the star of this language, always a context-free language as well. Again, you should be able to see, if you think of in terms of context-free grammars, you should be able to see that the answer to this question should simply be a yes. How? Again, considering in terms of context-free grammars, since A is a context-free language, there must exist a context-free grammar generating this language A, since A is a context-free language. Let's say let SA be the starting variable of this context-free grammar that generates A. Then we can easily come up with a context-free grammar for A star as follows: simply take all the rules corresponding to the context-free grammar for A and introduce an additional rule that says the following: S goes to epsilon or S followed by SA, and the rest of the rules for the grammar A. All of this grammar will now be able to generate A star. How? In A star, remember that we should always have epsilon, so we have a rule that says S gives rise to epsilon, so that's fine. And A star should also include all strings that belong to the language A that are concatenated any number of times we want, and that can be achieved through the second rule, S followed by SA. This way you can repeat SA as many times as you want, which will correspond to basically concatenating as many strings from the language A as we want. So the whole of this grammar, including this new rule and the old rules of the grammar corresponding to A, will give rise to a grammar, a context-free grammar that generates A star. So in this case, then new CFG, new context-free grammar, generates A star. Remember that with these three dots in the previous examples as well, we are actually considering this corresponds to the rest of the rules corresponding to the grammar for the given language A. So the whole of grammar consists of this new rule and the old rules generating A. So now so far we have considered three operations: union, concatenation, and star, and we have seen that the context-free languages are claused under each of these operations. Let's now consider yet another operation, yet another important operation defined on sets. So now let's consider the intersection operation. Again, the question is the same: are the context-free languages claused under this intersection operation? And we can pose it in terms of sets or languages as follows. Let two languages A and B be any context-free languages. Context-free languages. Is A intersection B always a context-free language as well? This is the question. So if this is true, then we will also say that context-free languages is claused under the intersection operation as well. We will see that actually for this operation, for the intersection operation, the same does not hold, that the class of context-free languages is not claused under the intersection operation. So the answer to this question is no. A intersection B is not always a context-free language, even though A and B are context-free languages. And the way to see that the answer to this question is no is the following counterexample, is through providing a counterexample. Consider the following languages. Consider A to be the following language. A is 0 to the m, 1 to the n, 2 to the n, such that n is greater than or equal to 1, let's say. And consider similarly the language B as 0 to the n, 1 to the n, 2 to the m. Now, the first language A corresponds to the strings. It includes all the strings such that it starts with any number of zeros followed by n zero ones, which are followed by exactly the same number, n twos. Okay, so zeros, a number of zeros followed by n ones followed by n twos. So in this case, number of ones and twos are expected to be the same. For B, on the other hand, n zeros are followed by n ones followed by any number of twos. So the strings in B have the condition that number of zeros should be the same as number of ones. Number of twos can be anything. Now, remember that both of these two languages are context-free. So A is a context-free language because we can easily design a PDA that will recognize such a language. How would such a PDA be informally? We would simply skip all the zeros that we see at the beginning of the input string, so we don't do anything specific for these zeros. Once we start seeing ones in the input string, we can actually push a symbol 1 corresponding to every one that we see in the input string into our stack, so that at the end of the ones in our stack we will have n ones. Now once we start processing the symbols 2, now for every symbol 2 that we read from the input string, we can actually try to pop a symbol 1 from the stack, so that at the end of the input processing, if in our stack all the ones are emptied, if all the ones are finished and we are at the end of the input string, then we will accept such a string because we will know that number of ones is equal to number of twos. We can use a similar idea to construct a PDA that will recognize this language B as well. So it's easy to see that both of these languages are context-free languages. However, it's also easy to see that their intersection, which is, note that A intersection B will be defined as the following language, since A requires that number of ones and twos to be equal, and B requires, on the other hand, number of zeros and ones to be equal. In their intersection, we will have the number of zeros, the number of ones, and the number of twos each to be equal. because number of zeros and ones is required by B, number of ones and twos to be equal is required by the condition required by the language A. So this is the definition of A intersection B, and in our previous class, in our previous lectures, we have seen that this language is not a context-free language. A intersection B is not a context-free language. We have proven this, that this language is not context-free, using the pumping lemma for context-free languages. So proven using pumping lemma for the context-free languages. To see this, you can check our previous video lectures. So actually, all of this discussion tells us that there can be two languages A, B, such that whereas both of them are context-free, their intersection is not a context-free language. This implies that the context-free languages is not closed under the intersection operation. Let's see further common operations defined on sets or defined on languages. Yet another common operation is complement. Again, we can ask the same question. Let A be a context-free language. Let A be a context-free language. Is the complement of this language always context-free as well? Is a complement always a context-free language or not? Again, the answer to this question will be no, and to see this, we'll actually make use of the result that we have found regarding the intersection operation. We can actually define the intersection operation using the complement operation and the union operation. How? We should know that A intersection B is equal to actually A complement union B complement and the complement of the union. You must remember a similar rule from propositional logic, which was De Morgan's rule. So A intersection B is equal to A complement union B complement and the complement of the union. Now, what does this tell us? Let's start with our statement. Let's say that let A and B be two context-free languages. If the answer to this question was yes, in other words, if the class of context-free languages were to be closed under the complement operation, if the answer were yes, the answer were to be yes, in other words, the class of context-free languages were to be closed under the complement operation, then since these two are context-free languages, then A complement and B complement would be context-free languages as well, would be two context-free languages. And since we have seen that previously, we have proven that the union operation, so context-free languages are closed under the union operation, this would also imply that A complement and B complement union would also have to be a context-free language. Also, A complement union B complement would be a context-free language, since we have already seen that context-free language is closed under the union operation. And finally, since we are assuming that the answer to this question were to be yes, then the complement of this language, of this context-free language, would also have to be a context-free language. Also, A complement union B complement, the complement of this union would also be a context-free language, which would be a contradiction because we know that this is now equal to A intersection B. So A intersection B would also have to be a context-free language. However, we know that we have just seen that this is not always true, that the context-free languages are not claused under the intersection operation. So now we arrive at a contradiction. Since A intersection B would be a context-free language, which we have just seen that is not always possible. So this whole discussion implies that the complement operation is not claused. So context-free languages are not claused under the complement operation, because if it were, then the intersection would have to be the same. Context-free languages would have to be claused under the intersection operation, but we have just seen that this is not true. So context-free languages are not claused under the complement operation. Let's now see yet another common operation defined on sets and defined on languages. Let's talk about the difference operation. So we can ask the similar question. Let two languages, A and B, two context-free languages, let A and B be two context-free languages. Is A difference B always a context-free language? Again, the answer to this question is no. This is not always true, that the context-free languages is not claused under the difference operation. How do we see this? Again, we can start with, let's start with a context-free language A. Let A be a context-free language. We already know that the star of an alphabet is already a context-free language. So sigma star for any alphabet sigma, finite alphabet sigma star is a context-free language. Basically, sigma star is the language that contains all the strings composed of the input symbols in the alphabet. You can easily construct a context-free grammar for such a language, sigma star. So this is always a context-free language, and it's easy to see that we can define actually the previous operation, the complement operation, in terms of the difference operation. So A complement is actually equal to sigma star, basically the universal set, minus A. Okay? So the complement of a language is basically any string in our universal set that is not already in the set A. Now, if after this operation we get a context-free language all the time, meaning that if the context-free languages is claused under the difference operation, then this language, a complement, would have to be also context-free. So if the answer were to be yes, if the answer to this question, if the answer were yes, the answer to this question were to be yes, then sigma star minus A would have to be a context-free language. Since A is assumed to be context-free, sigma star is already context-free, and their difference would have to be a context-free language as well, which would imply that A complement would also be a context-free language. However, we have just seen that this is not always true, that the complement of a given context-free language is not always a context-free language, so we would arrive at a contradiction. So this is a contradiction since a complement may not be context-free language, even though A is a context-free language. We have just seen this within the discussion regarding the complement operation. This implies that then the context-free languages are not closed under the difference operation either. So to summarize, we have seen three operations, union, concatenation, star, such that the context-free languages are closed under these operations. And we have also seen three other common operations, intersection, complement, and the difference operation. And we have seen that the context-free languages are not closed under these operations.